So there are some problems where I want to say you get stuck in this endless loop, and we call this a cyclic integration. And a cyclic integration occurs when you integrate multiple times. And what happens is eventually you get back to having an integral, which is exactly the same original problem that you're asked to integrate. So this happens a lot, especially when you're dealing with exponential functions and trig functions, or logs sometimes with exponentials. But let's take a look at A. You have an exponential function and a trig function. So by my phrase light, the trig function cosine comes before the exponential function. So I'm going to let u be equal to cosine of x. My dv is going to be my e to the x. So my du is going to be negative sine x dx. My v, the integral of e to the x, is just an e to the x. So I want to plug it into my parts. So u times v minus your integral v du. So u is cosine x, v is e to the x. So I have e to the x times cosine x minus your integral of v, which is an e to the x, times my du, which is a negative sine x. So if I pull the negative sign out, that's going to turn that into a plus sine x dx. So again, I just pulled the negative sine x in front of the integral, which made this a positive. Notice right here, you're stuck again. You have an exponential and another trig. So what we have to do is we have to do integration by parts again. Again, you have another exponential function, you have a trig function. This e to the x cosine x is just tagging along to the final answer. So again, I'm going to have to let u be equal to sine x. My dv is equal to e to the x. Well, the derivative of sine is a cosine x. My integral of e to the x is just an e to the x. So plug it into my parts of it again. U times v, so I have e to the x sine x, minus your integral of v times du. So v is e to the x, du is cosine x. And there should be a dx there. Notice this e to the x cosine x dx is my original problem. So what I have here is I have that e to the x cosine x that was tagging along, plus your e to the x sine x, minus your e to the x cosine x dx. So when you get back to the original part, again, this is my original problem. So I'm going to set this equal to what I'm trying to integrate, to the integral of e to the x cosine x dx. So now what I'm going to do is I'm going to collect my like integrals on one side of the equation. So I'm going to add this integral of e to the x cosine x to both sides. So when I add these two integrals together, that's going to be 2 times your antiderivatives e to the x cosine of x dx. Now remember, you're trying to solve for the integral of e to the x cosine x. So I'm going to divide both sides by 2. So then your integral of e to the x cosine x dx is equal to e to the x cosine x plus e to the x sine x all over 2, and don't forget to add your c. So when you get that integral, when you get back to the original problem, you want to collect the like integrals on both sides. So here is, now this is not a product, this is a composition. You have the sine of the natural log of x. So this all has to be my u. My u is going to be equal to the sine of the natural log of x. My dv will just be my dx. So my du, I have to use my chain rule. The derivative of sine is going to be a cosine of the natural log of x times the derivative of natural log of x, which is 1 over x. So there's my du. My v is just going to be x. So I'm going to plug it into my parts, u times v minus your integral of v du. So u times v, so that's going to give me x times the sine of the natural log of x, minus your integral of v, which is x, times your du, which is the cosine of the natural log of x over x dx. So now again, these x's are going to cancel out, so I have x times the sine of the natural log of x minus your integral of cosine of the natural log of x dx. So right here, you're stuck again. You have cosine of the natural log of x. You have to do parts again. Again, u will be equal to the cosine of the natural log of x. My dv is just my dx. So my du, have to use my chain rule again, is going to be a negative sine of the natural log of x times 1 over x. My v is just going to be my x. So now I have x times the sine of the natural log of x. Now you need to be careful with the subtraction sign. The next part is your parts following the subtraction sign, so you have to make sure you put parentheses around this u times v minus your integral of v du, your parts section again. So we have u times v, so that's going to be x times the cosine of the natural log of x, minus your integral of v, which is your x, times your du, which is going to be the negative, so I'm going to pull that negative sign out, that's a plus, sine of the natural log of x all over x dx. So now if I clean up this integral, I know the x's are going to cancel. Now notice the sine of natural log of x, I am back to where I started from. So I need to distribute this subtraction sign. So I have this x, sine of the natural log of x, minus x, cosine of the natural log of x. So remember, this became a plus, so I distribute, that's a minus integral of sine of the natural log of x dx. So now, since I'm I'm back to exactly the same integral as what I started with. So what I want to do is I want to isolate. I'm going to set this, so x sine of the natural log of x minus x cosine of the natural log of x minus your integral sine of the natural log of x dx is all equal to my original integral, the sine of the natural log of x dx. What I want to do is I want to add, I'm going to combine like integrals on the same side of the equal sign. So x times the sine of the natural log of x minus x cosine of the natural log of x is going to be equal to, when I add the like radicals together, the like integrals together, that's going to give me a 2 times the integral of sine of the natural log of x dx. Now to solve for this integral, I can divide both sides of the equation by 2. So x sine of the natural log of x minus x cosine of the natural log of x all over 2 plus c is equal to that sine of the natural log of x dx. So again, that's what happens when you have that cyclic integration. Now there is, in some cases, a quicker way to do integration by parts, and that's by a tabular method. So if you have an integral in the form of p of x times f of x, where p of x is a polynomial, so one of your functions in your integral has to be a polynomial, it can be evaluated by using repeated integration, because what happens is p of x, or one of its derivatives each stage, again, since du is the derivative of u, eventually becomes a 0. So basically, when you take the derivative of the polynomial, you'll basically take the derivative down to a 0. So this would basically be a repeated integration by parts problem. The tabular method makes it a little bit quicker when you'd have to do parts over and over again in a problem. So a convenient method for organizing this is called tabular integration by parts. So the way this works is, first of all, whatever function is your polynomial, we're going to differentiate until you get a 0. And then you're going to integrate the other function in the second column. And then you're going to draw an arrow from the first column to an entry in the second column, but one row down. You're going to label your arrows with an alternating positive and negative, starting with a plus sign. And again, what you're going to do is you're going to then start multiplying and adding the different terms together. So for example, here's the integral of x squared minus x times cosine of x. So here is your p of x. Here is your polynomial function x squared minus x. Here is your trig function. So what you're going to do is you simply just differentiate x squared minus x until you get down to a 0. So this is my d dx. The other function you integral, you're going to integrate. So integral cosine sine, integral sine negative cosine, integral negative cosine negative sine. Label your arrows starting with a plus and alternate plus, minus, plus. So now what you're going to do is you're going to multiply the two functions that the arrow is connecting. So again, it's going to be x squared minus x times sine of x. And it's a positive coefficient. So here now it's going to be a minus 2x minus 1 times negative cosine of x. And then it's going to be plus 2, because that's a plus, times negative sine of x, plus c. So if I clean this up, that's going to give me x squared minus x times sine of x. Again, these two negatives become a positive, so plus 2x minus 1 cosine of x minus 2 sine of x plus c. So that's the way your tabular method works. So for example, let's look at a. So anytime you have a polynomial in your integral as part of your product, you can use tabular over integration by parts. So here's my x to the fourth times e to the x. So x to the fourth is my polynomial function, so I can set up my table. My first column is I'm differentiating. My second column is I'm integrating. So again, you're differentiating the polynomial. So you want to take the derivative of x to the fourth enough times till we get down to a 0. So I take the derivative of x to the fourth, it's a 4x third. The derivative of 4x to the third is a 12x squared. Derivative of 12x squared is a 24x. Derivative of 24x is a 24. There's my 0. I want to integrate e to the x over and over again as many times as I took that derivative. And I know the integral of e to the x is just e to the x. So now I'm going to draw my arrows. So I'm going to draw my x to the fourth. Down to the second row, I start with a positive. Alternate your signs. That's a negative. Positive, negative, positive. So now we're going to put all these together. So I have x to the fourth times e to the x. I have 4x to the third times negative e to the x. So negative 4x to the third e to the x. 12x squared times e to the x. 24x times negative e to the x, which will be minus 24x e to the x. And then finally 24 times e to the x. And then plus your constant. So that's how your tabular method works.